Okay.
Look good? About like here?
What?
Is it about like here?
I don't know. A couple of my buddies are saying something like
Playable?
that. I hope so.
Kind of.
We got to wait today. Between Thursday and so tomorrow.
Is it on the bus?
Yeah.
Oh, that's a long drive.
Yeah.
Well, still have one more minute. So this is not the quiz coming around, but just an assignment for Thursday. So the question sheet you have in your hand is this file, and then the article for that is here. So it's about 1.5 pages, not very long, but just to help with some of the Chapter 7 concepts. So yeah, Lainey, the article you have there is just this reading, about 1.5 pages, and then just answer the questions for Thursday. For other stuff, for today, we'll be into a new spreadsheet. Don't toss the previous spreadsheet because we're coming back to it in Chapter 8. But for today, new data, new spreadsheet. It's right here. Effect size calculations, and then Chapter 7. So just under the February 21st lecture materials. From the previous week, we'll have all of our February 16th is here. So, hello, Bailey. Thanks for coming. So this is due on Thursday. There's an article within the February 21st folder for this. Okay, so it's 2:01. Let's go ahead and begin. All right, well, welcome. Thanks for braving the weather and coming out. So a couple things. We have announcements, and then a quiz, and then Chapter 7 stuff. And then we're a little bit ahead of schedule, so we may even get into Chapter 8 Thursday. So let's look over the course outline. So we are here. I think I've got the city certificate from almost everybody. Your grades should be entered. If it's not, let me know, and I'll update the grade book. So mostly Chapter 7 this week. Next week we get into Chapter 8. We may even get Chapter 8 on Thursday. Research proposal due March 2nd. Make sure you ask if you have questions. All the materials there. If there's something that needs to be clarified, just let me know. Then we have a nice break. Coming back on Tuesday the 14th. It's a little bit of a gap. So I'd like to do a review activity for that before we go to Exam 2 on the 16th. As soon as we get back from break, you should have feedback on your proposal, and you should be good to go as far as recruiting participants. So some of you athletic teams, others of you coming to KIN 105 or other classes. So in KIN 105, it's a requirement to participate in at least one research project, and so that's a great source of participants for a lot of you with the studies that you're doing. I'll recommend that you jump on that right away. There are 31 kids in KIN 105. I want you to have the first crack at getting participants. So if you're not utilizing one of the athletic teams, then probably coming to KIN 105 is your best source of participants. So you want to jump on that right away, and then probably from about mid-March to mid-April, every one of my Fridays is going to be dedicated to data collection in some way. So Dr. Schaefer and I will have a conversation about blocks of time within the lab. I know some of you are not going to be collecting data in room 134 downstairs, but a lot of you are. So as soon as we get back that week, we're going to start talking about organizing all of that, where you're going to be for your data collection, and then creating a schedule so that all of Dr. Schaefer's students and my students can have the time to collect data. So that's things to tackle when we get back from break. You will need an informed consent. It's not your final one, but it's a practice. So you'll have that for your thesis when the time comes. You don't need to go through the whole IRB process. It's just a small class project. So as said in the requirements, just 3 to 5 people. It's just a pilot study. You're just kind of seeing trends, reporting means and standard deviations. Although a lot of you, because you're involved with athletic teams, you're pretty much going to have a good sample of 10 to 15 people, which is fine. So we'll talk about maybe going one step further and doing the stats for that analysis. So do you have any questions? Yes?
So just in the email that you sent out the other day, you said that the research proposal was due on Friday the 2nd, but it looks like the 2nd's on Thursday.
I'll give you another day.
Okay.
Yeah, because I probably wouldn't, even if you turned it in the 2nd, I probably wouldn't read it till the 3rd. So, yeah, another day. So we'll make it Friday, March the 3rd. How's that? Okay, so the next item on the agenda, so quiz, looking over confidence intervals. So we had some actual data, and we did some confidence intervals. So if you're drawing a sample from a population, you don't expect the sample mean to be the same as the population mean. So the confidence interval gives you an idea of the range within which the population mean is likely to be. So we can set limits that have a 95% certainty. We can set limits that have a 99% certainty. So if it's 99% certainty, the limits are going to be a lot wider. If it's 95, it's going to be a little less. So with that in mind, pull up that spreadsheet, and you'll probably need some type of calculator so you can calculate those limits. But just a quick quiz. So we pretty much did the first one on the bodybuilders together. Just fill in those numbers. So should be pretty quick for you. Give you 5 minutes or so. I didn't bring any extra calculators, so you can use like a cell phone application or whatever you have. That's a link. The one you sent me was good. Look up the one you sent me. If you're all finished, you can just raise your hand and we'll come around and. Thank you. No, it just had to be done. I appreciated some people sent it to me, and that was really nice. But just had to use it for the quiz today. A couple more minutes to finish up. It's the very end of 6. Okay, thank you. Has everyone received the Ray questions? So those will be due on Thursday. Let's go ahead and continue with chapter 6. So we left off talking about the confidence interval. So the limits above and below the mean in which you're most likely to find the mean of the population. So because the mean of the sample and mean of the population are likely to be different. Table 5 from the text. I saw lots of you with table 5 out. And so based on the degrees of freedom, and what's degrees of freedom equal to? Yeah, n minus 1. So the number of people you have in your sample minus 1. And the reason we use n minus 1 is because we get a smaller number, which means that it's more likely to approximate what you would get for the population versus just the sample. So then you go across, and what's the probability we always use within this field for research? P is equal to what? 0.05, that's right. So that's the standard, and so we go to the value in table 5 that shows us the 0.05 probability level. So we're 95% certain that the population mean lies within those limits as specified by that number. So the standard error, okay, multiplied by the value in table 5 gives us the confidence interval above and below the sample mean. So if we want to be a little more, I guess we want to be a little bit broader range would help us to be 99% sure of where the population mean is at. So the value in table 5 would be a lot bigger to multiply by the standard error. Okay, so now we come to the normal curve, and so there's lots of human traits and measurements that approximate a normal curve. You can see things like weight, height, strength, body temperature, intelligence, things that we measure as part of health and human performance. If we have a large enough group, then the scores that we get start to approximate what you see here. So sometimes called the bell curve or normal curve. So in this case, all the measures of central tendency, so the mean, median, and mode, are equal and at the center of the distribution. So when we look at the variability from the center of the distribution, so we can say that about 68% of scores are going to be plus or minus 1 standard deviation from the middle. So on each side, if we take each side 1 standard deviation, plus and minus, would have 68% of people. If we go out to 2, we're taking in 95% of scores, and then almost 3 would be 99% of scores. So do you remember the question on the exam? Someone is about 3 standard deviations above or below the mean. What do we define that as? So really out there. Outlier is right. Good. Okay. So when doing parametric analysis, we have to have 3 different assumptions. And so for research in our field, we assume that these have all been met. So the first one is the population from which the sample is drawn is normally distributed on the variable of interest. Second assumption is that the population has a similar variance to the sample on the variable of interest. So variance or variability. So standard deviation is how we measure the variability within a sample or population. Third one is the observations are independent. So what that means is when we measure a characteristic on an individual, that measurement doesn't have any influence on subsequent measurements. So if we're measuring vertical jump height on Corey, that wouldn't affect our measurement of vertical jump height on Eric, is what that means. So independent observations. So most research in physical activity, towards the end of chapter 6, there's a good paragraph on this. We just assume these assumptions have been met. That's the easy approach. And because we often use samples of convenience, really, that's about all we can do, is just assume that these assumptions have been met. But it's important to know what they are. Okay, so what statistical techniques tell us is the significance. Significance is based on probability. So can we say significantly different? If our alternative hypothesis is true, and there are real differences between the experimental group and the control group, what is the probability of real differences? And so typically we adopt the 0.05 value. So in other words, 95% of the time, differences between groups are going to be real or true. So then we have the other 5% of the time. So 5% of the time, differences are not real, they're due to what? Random or chance occurrence is what. And that's really what significant means, is the probability that differences between groups are due to chance. Right? So that's what we say, P is less than or equal to 0.05, the probability that differences between groups or conditions are due to chance. That's what significance is defined as. Meaningfulness. So this is where we take one step further. So just because something is not statistically significant doesn't mean that it's not meaningful or practical. So if we have a very small sample, it's going to be very difficult to demonstrate statistical significance. However, if you look at the difference over time or the difference between conditions, it still can have some meaningfulness. So I don't know anybody that if you said, well, if you do this, you'll improve your 40-yard dash by 0.4 of a second. And if you knew that you could go from, if you're training for the NFL Combine and you're currently sitting at 4.7, and you knew that you could go down to a 4.3, does that matter? It matters a lot. So it may not, going from 4.7 to 4.3 may not be statistically significant, but definitely meaningful. So meaningfulness is different than significance, which is based on probability. So types of techniques, so relationships, descriptive. So we'll get back into Pearson R, which is how we calculate correlations. We'll get back into that on Thursday with chapter 8. Differences between groups, conditions, or time points. So difference between an independent t-test versus a dependent t-test. Dependent t-test is the same person measured at different time points, so pre versus post. Independent t-test would be a comparison of different groups or different conditions. So in each case, you can't have more than 2. So 2 time points, 2 conditions, 2 groups, independent or dependent t-test is appropriate for just 2. If you go beyond 2 and you have more than 2 groups or conditions or time points, then that's where we go into ANOVA. So we'll get into ANOVA in chapter 9, I believe. So and that's nice, because it's nice to be able to go beyond. So wouldn't it be nice, rather than to do just a pre and a post, in some studies, maybe if it's a 16-week study, wouldn't it be nice to have a midpoint in there as well? So the halfway point. So that's where ANOVA comes in really handy, is you can go beyond just 2. Okay, so cause and effect. So one of the benefits of correlation is to just explore to see if there's any association between variables. So it's the first step in establishing cause and effect. If 2 things are highly correlated, it creates interest, but we don't say that one causes the other or one causes an effect in the other. But a strong association suggests that we should do some further research, is the bottom line. So do you have any questions on chapter 6? So do you understand variance, standard deviation, significance, confidence intervals? Okay, all right, so let's keep going then. Chapter 7. Okay, so basic statistics and research. Okay, so probability. As I think about this chapter and reflect on it, I think the point of the whole chapter is, are we making a correct decision? So we collect data and we do an analysis and we interpret that analysis, and then we make a decision about the difference between conditions or time points or groups. The whole point is our decision correct? And so probability, we use statements to describe our confidence that our decision is correct. So if a value of p less than or equal to 0.05, how confident are we? We're 95% confident that we made the correct decision. I'll take that. That's pretty good odds, right? So 95 times out of 100, if you conducted that same experiment, you would get the same result. So the other 5% is when we run into problems. But I'm willing to accept if there's a 5% error in our decision making, that's pretty good. That's pretty accurate decision making. Okay, so level of chance occurrence, typically p less than or equal to 0.05, 95% certain that the results did not occur by chance. So the 0.05 is sometimes referred to as an alpha level. So as you move on and you write your thesis, in your statistical analysis, you'll say the alpha level or probability level was set at p less than 0.05. So alpha level and probability level, they mean the same thing. So alpha is just a way of expressing your probability value of 0.05. So I want you to think about this. What if we don't make the correct decision? So that 5% of the time, differences between groups or time points or conditions is due to random chance occurrence. So in this case, there's a failure to reject a true null hypothesis. Okay, so let's put that aside for a minute. What is the null hypothesis? What does it tell us? So you all did really well on the exam on this part. What is the null hypothesis? So differences between groups, conditions, or time points. No. Yeah, no difference between groups, conditions, or time points, right? Okay, so if the null hypothesis is true, okay, so there is truly no difference, and we fail to reject it. Okay, so we fail to reject it. We've made an incorrect decision, right? Okay, so if the null hypothesis is true, meaning there's no difference, and we fail to reject it, that means we've made what's called a type 1 error. Type 1 error. We've made an incorrect decision. Okay, so the statistical test indicates there's another way of viewing a type 1 error. Type 1 error is a statistical test indicates there is a difference. Okay, so our statistical test says yes, there's a difference. When truly or in reality there is not a difference between groups or experimental conditions. So this is when differences are due to that random chance. So 5% of the time our statistical test says yes, there's a difference, but in reality there is not. So this would be considered a type 1 error. So we could also say that p less than or equal to 0.05 is the chance of making a type 1 error. The chance of making a type 1 error. When the stat says there is a difference, but there's really not. So 5% of the time that could happen. So yet another way of describing this would be a false positive result. When you say there's a difference, but there's really not. So it's a false positive. Okay, so our typical probability, p less than or equal to 0.05. We want to be a little more strict, 0.01. So with 0.01, what would be the chance of making a type 1 error? What percentage of the time? 1% of the time we make a type 1 error. Okay, so that's really strict. It's a little harder to achieve that. We'll talk about reasons for that later on. So again, 5% or 1% of the time, the stats says there's a difference when there's really not, and the null hypothesis is true. Okay, so what about type 2 errors then? So there's a type 1 error and a type 2 error. So type 1 error means that our stat says there's a difference when there's really not. Okay. Type 2 error is failure to reject a false null hypothesis. So if the null hypothesis is false, what does that mean? If the null hypothesis is false, there are differences, right? That's right. So if the null hypothesis is really false, there are differences, and we fail to reject a false null, we've made an incorrect decision. So there's two cases where you make an incorrect decision. One of them, your stat says, yes, there's a difference, but there's really not. The other one, type 2, the stat says there is not a difference, but there really is. Type 1 versus type 2 error. So sometimes, like type 1, an error is called a false positive. A type 2 error is sometimes called a false negative. Okay, so let's think about this. Type 2 error. So there could be negative consequences, especially if you're testing a drug that maybe could be useful for a cancer treatment, right? Think about that in the context of a type 2 error. When your statistical test on that drug versus a control says there's no difference, but in reality, there is a difference. So as you can see, a type 1 and type 2 error, both of them are associated with negative consequences. So a key point, as the alpha is set increasingly smaller, okay, reducing the chance of a type 1 error, the chance of making a type 2 error becomes increasingly larger. So as we go from 0.05 down to 0.01, there's less chance of making a type 1 error, but we also may not be picking up on those subtle differences between conditions that would be associated with a type 2 error. Okay, so how does this all tie into health and human performance? Let's take an example. So a screening test. How many of you have ever taken a screening test? Okay, why do we use screening tests? Like, how many have done the functional movement screen? Okay, if you've had kinesiology, you've done the whole thing. Okay, so we did that last fall if you had kinesiology. So why do we do the functional movement screen then? The FMS. What's the purpose? Okay, well, we want to be able to tell certain things about you, don't we? Okay, we want to maybe, is there any association between what we see in the functional movement screen and perhaps future risk of injury? Yeah. So that's generally the functional movement screen is just one example of a screening tool. Yes.
So you're using it to set a baseline, or is that not?
Not necessarily setting a baseline, but what you're trying to see is, okay, well, if I see abnormal movement during the functional movement screen, that could be associated with an injury sometime down the road. So we call those movement compensations. So a movement compensation is different than a normal movement pattern. So it'd be an inefficient movement pattern. And so there would be various problems or muscle imbalances that would be causing the inefficient movement pattern. So we say, okay, well, if there's an inefficient movement pattern, then maybe sometime down the road there would be an injury caused by the inefficient movement. Does that make sense? Okay, so a screening test can be used to predict probability of an injury given a certain score. So the functional movement screen has 7 tests, and each of them are worth 3 points. Okay, so research has indicated that a score of 14 or less is associated with a future incident of injury. So there's a certain probability or risk with a certain score on the functional movement screen. Okay, so in order to understand screening tests, we have to understand these 4 different observations. So a true positive, false positive, true negative, and a false negative. So we're going to set this up with a 2x2 diagram to show you each of these scenarios. Okay, so what we have over here is the reality. Okay, so injured versus uninjured. Okay, so these 2 rows, everyone within these 2 columns along this first row would represent a person that suffered an injury. Okay, so down here, everyone in the second row in these 2 columns didn't have an injury. Okay, so this is the reality. People that were injured, people that were uninjured. And let's say we have this entire group and we did a screening test. Could be any, maybe the functional movement screen, maybe another screening test. Okay, so within the first column here, we have those that screened positive. Okay, so that means yes, there's a high probability that they're going to suffer an injury. In the second column here, they screened negative. So they took our test, again, whatever that might be, and they screened negative, meaning our test said that there was a low probability of injury. So what we have is a comparison of the reality, those that were actually injured or uninjured, with our screening test. Those that screened positive and those that screened negative. So a high likelihood of injury, a low likelihood of injury. So we have 4 different scenarios. So those that had an injury who screened positive. Okay, so that's a true positive result. Our screening test said yes, and then unfortunately they did end up having an injury. So that's true positive. Okay, so what if our screening test said no? So the beginning of the season, our screening test says no, they have a very low likelihood of injury, but unfortunately they have an injury anyway. So that would be what's considered a false negative. Our screening test said no, but unfortunately they incurred an injury. Is everybody with me so far on what this means? Okay, so uninjured then. So let's say our screening test says yes, they have a very high likelihood of injury. Okay, so screening test says yes, but fortunately they did not incur an injury. Okay, screening test says yes, but they didn't. Okay, that would be considered a false positive. So screening test says yes, but they didn't have an injury. That's a false positive. And then lastly, our screening test says no, and they did not. So does everybody understand those 4 different boxes? So the correct decision is here. and here. Okay, so the correct decision, so, okay, screen positive. Unfortunately, yes, they did have an injury. Okay, so that's the correct decision. That's the way a screening tool is supposed to work. Alternatively, our screening test says no, they're at low risk, and they did not. So these two boxes, true positive and true negative, that's the way a screening test is supposed to work. But that isn't always the case. Like just with anything else, tests aren't perfect, right? So we want to have tests that are able to correctly identify individuals that are at risk and correctly weed out individuals that are not at risk. That's the ideal screening tool. But screening tests are not perfect. So this is where we make correct decisions if it's true positive or true negative. But we also have situations where we have incorrect decisions, false positive. Remember type 1 error? When our test says yes, but what actually happens in reality? So our test screened positive, but they did not occur an injury. So what's the problem with that? If your test says this individual is at super high risk of injury, okay, but then they don't have an injury, what's the problem with that? So at the beginning of the season, you say, okay, based on their movement, they're at very, very high risk. Would you treat them differently versus someone who screened negative? Yeah, okay. You might spend an inordinate amount of time trying to correct these movement compensations that have nothing to do with whether this person will have an injury or not. Okay, so that would be a type 1 error. The tool that we have says yes, but in fact, they're not at disproportionate risk. Okay, the other scenario would be a type 2 error. So this would be our screening test says no. So what we observe with a screening test, they're not at high risk, but they actually do have an injury there. So this is why screening tools are so important. Do we want to choose one screening tool? And that's the reason why. It's because if you just use a single screening tool, chances are you're going to make a lot of type 1 and type 2 errors. So we use multiple screening tools because then we can get a better overall picture of identifying people that are truly at risk versus people that are not at risk. So a type 2 error would be when our test says no, they're not, but in reality they actually are. So we have to use multiple screening tools to determine whether an individual is truly at risk or not. Okay, so a couple of terms here, sensitivity and specificity. Okay, so sensitivity. So sensitivity tells us how well we can identify people that are truly at risk. So it's defined as percentage of people who had an injury and tested positive with the screening. So it's basically your percentage of true positives. So if you took all the people that had an injury and figured out how many of that total group that your test flagged as positive, that would be sensitivity. So specificity, on the other hand, has to do with up here. So percentage of people who did not have an injury and did not test positive with a screening test. Okay, so the number of true negatives. So if you took all the people in the group that did not have an injury and you figured out the percentage of those people that did not have an injury that screened negative, that would be specificity. So both of these are really important. So if we have a really good test, we can identify people that are truly at risk, that's sensitivity, and we can identify people that are truly not at risk. So that would be your specificity, at risk and not risk. So sensitivity, thought of another way, probability of a test to correctly predict an injury among all those who had an injury. Okay, so this is how we calculate it right here. So the number of true positives divided by the total number of people that had an injury. So adding up your true positives plus your false negatives. So basically what we're doing is we're just taking all the people that had an injury, we're taking the true positives and dividing it by the sum of everybody up here across these two rows. Okay, so implications are a test with poor sensitivity would incorrectly place many athletes into a low-risk category. So we don't want to do that. We want our test to be able to identify those that are truly at risk. They shouldn't be placed in a low-risk category so that we can do something about it before they have an injury. Okay, so specificity, on the other hand, quantifies the ability to screen out individuals that are not at risk. So here's how we calculate it. It's taking all the true negatives, so your test says no, your test says no, and then we're dividing it by the total number of people that did not have an injury. So true negatives plus false positives. So if we have very few false positives, then our specificity percentage is going to be really high. So our test is able to clear individuals that are truly not at risk. So it's important to have high specificity so that we don't incorrectly categorize someone into a high-risk category. So implication, so this may result, if you put somebody in a high-risk category that's really not at risk, they could be spending all this time doing corrective or injury prevention exercises when they could be spending time doing a lot of other things for other characteristics. So time is so important. So we want to make sure people are using their time with the greatest benefit. Okay, so some of you may have this coming up. So parsing or interpreting a statistician's response to a marriage proposal. Okay, so I couldn't resist, I had to put this in here. So I failed to reject the null hypothesis. Okay, so what's the null hypothesis? Is there a change in status or no change in status? There's no change in status. You fail to reject. The no change in status means the status does what? Status stays the same. If you fail to reject a situation where there is no change in our status. So, oh no, that means no, the null hypothesis is negative, and you fail to reject the negative leaves it in place. Okay, so meaningfulness. So what about going beyond statistical significance? So going from a 4.7 down to a 4.3. May not be statistically significant, but practically it's definitely, that would make a huge difference in your ability to get drafted into the NFL. So the practical significance of an effect or relationship. Okay, so this is how your statistical section would go, writing in probability and effect size. So I want you to read this. This is from a previous study on blood flow restriction. The level of significance was set at p less than 0.05 for all statistical comparisons. Okay, so you state the probability up front. Additionally, to determine the magnitude of the findings, effect size, okay, so effect size, ES, the difference between pretest and post-test scores divided by the pretest standard deviation statistics. So effect size statistics were calculated for the systolic blood pressure and diastolic blood pressure responses for each resistance training session using the scale proposed by Ray. Okay, so that's the article that you have in hand. So this article right here is what this reference is referring to. So if you read the title, Determining the Magnitude of Treatment Effects in Strength Training Research Through the Use of the Effect Size. Okay, so you're going to read that article. It's about a page and a half. So the effect size represents a standardized difference. So the advantage is that you can take two studies that measured the same dependent variable. So it can be blood pressure response, it can be strength response, any two dependent variables that are the same between different studies. And you can calculate an effect size for each study for comparison, because the effect size represents a standardized difference. It represents differences in standard deviation units. So to calculate the effect size, this is copied from the Ray article. We're taking the post-test mean minus the pre-test mean divided by the pre-test standard deviation. So it allows a comparison between studies. And isn't that nice where we can take two or more studies on the same topic and we can put them into maybe one literature review? So the meta-analyses that you've read and we've read in this class, that's what they calculate is the effect size. So they can take a bunch of studies that measured the same thing and they can convert all of their results into a common metric, which is the effect size, and then you can make comparisons. So you can get a sense of what the body of literature is telling you because you can take multiple studies and calculate these effect sizes. Okay, so I'd like to do a few calculations here with some real data. So if all of you, if you want to go to this file, so this file, it's under right here, under February 21st lecture material. So it's this effect size example calculation. So if you could open that. And so we're going to do some effect size calculations. So we're going to practice that formula. Okay, so this is a study that was done back about fall of 2006. Fall of 2006 is where this data comes from. So it's comparing different rest intervals between sets on strength gains in the squat. So over 12 weeks, one group rested 2 minutes between sets, another group rested 4 minutes between sets, and then the pre and post values are shown here. So what I'd like you to do, we're going to go through this together, but what we need to calculate the effect size, we need the means and standard deviations. And then we can come up with an effect size for the 2-minute group and an effect size for the 4-minute group, excuse me. So take a look at this table. This is from the Ray article. And so what's nice about Ray is that he made different categories based on training status. And so in his article, he classified untrained versus recreationally trained versus highly trained. And so Ray classified untrained as individuals who have not been consistently trained for 1 year. Okay, recreationally trained was individuals training consistently from 1 to 5 years, and then highly trained was individuals training for at least 5 years. And so all three of those categories, and then the magnitude of the effect size. So how big is the effect size between two different groups or time points? And so trivial, small, moderate, and large. And what you notice is that what happens to the magnitude of the effect size for each category? Large, greater than 2 for untrained. Large is considered greater than 1.5 for recreationally trained. And large is considered greater than 1 for highly trained. So the reason for that is diminishing returns. What does that principle mean in the context of exercise? Diminishing returns. Diminishing returns. It's like a window is closing. So you've never lifted weights before, and then you start, and what are your results like? Are they good? Yeah, they're really good. Lots of gains to begin with very little time investment. Okay, so then you keep on training, and so after several years or even a couple of decades, what are your gains like? Not as good, right? How much more time do you have to put in? You have to put in a lot more time and a lot more creative programming to get even just the slightest amount of additional gain. So the principle of diminishing return says that with increased time, untrained, recreationally trained, highly trained, the window of adaptation, what does adaptation mean? What's another word for adaptation? Adaptation means change, changes that your body makes. So over increased time, the window for your body to make changes begins to close. And so there's increasingly less room for improvement, is another way to say it. So that is what Ray practiced here with greater effect sizes are expected for untrained, recreationally trained, and highly trained, especially over short time periods. So this particular study involved recreationally trained individuals. So we are going to be using the middle column here. The middle column. So recreationally trained. So Ray defined that again as individuals training consistently from 1 to 5 years. So you're going to want to pay attention to the middle column. Another note, it's important right here, take the absolute value of the effect size calculation. So let's say you get a negative 1.5 for your calculation. You want to take the absolute value of 1.5 in how you interpret that. Okay, so let's get into it. We're here. Let's do this together. Okay, so mean. So to get a mean, what's the first thing I need to do to enter a formula? Yeah, equals. Okay, and then you can just type average. Average. Open your parentheses. Okay, so you can see we started a formula. You can always check up here in the formula bar to see what's going on in that cell. So equals, average, open your parentheses, and then to make it easy, we can just highlight the cells that we want to include in that average. Close your parentheses. So we've got equals average, B3 through B9, right? So we're just going to take an average of these numbers. So once you've got that, you can hit enter. So that's the mean or the average. So what did we learn from last time if we want to make this really fast? If I wanted to quickly calculate the mean for this post time point, what could I do? Yeah, that's right. Good, Eric. So you could click, it's already there, so then you go here. You see how that cursor changed, where you have this now, and then you can just pull it across, and then you get that average for that other column. Going across like that. Okay. So it appears if you just look at the mean values, that you have a pretty good increase in strength. This is in kilograms, okay, kilograms, metric units. So 145.13 kilograms was the pre-test. The post-test, 12 or 13 weeks later, was 171.43 kilograms. So pretty good gains for 13 weeks of training for back squat with 2-minute rest intervals between sets. Okay, so standard deviation now. So equals, so what do I want to type in for a standard deviation? Yeah, ST, right, STDEV. Do I remember from last time I made that mistake? What do we want for this? Dot S. Yep, just like that, so then you open your parentheses there. Okay. So STDEV dot S, open your parentheses, and then you just highlight the cells that you want that standard deviation, just like that. Close the parentheses, and hit return. So at the pretest, the mean was 145.13 kilograms. That was a max, plus or minus variability, right? 24.17 kilograms. Okay, so the same idea, you can click on that and you can drag across like this. And so now you have the pretest means, and you have the pretest standard deviation and the post-test standard deviation. Okay, so any questions on this at this point? Okay, all right, so let's go ahead and calculate the effect size now. So let's go ahead and just calculate the effect size just for the 2-minute group. Okay, so first thing, like we always do, we're going to hit equals. Open parentheses. Okay, so what's the formula? Look back into the PowerPoint. What's the formula for effect size? Yes, so post-test mean minus pre-test mean divided by the pre-test standard deviation. So you can just click all the values that you need here. So post-test, right, minus the pre-test. So I'm just clicking on the values that I need. So post-test minus pre-test. Okay, and then put a slash. And then you'll click on the pre-test standard deviation. Just like that. So all I'm doing is just clicking on the values that I need in that formula. Post-test minus pre-test divided by the pre-test standard deviation. Okay, so that will give you your, let's see, went wrong there.
I don't think you closed the parentheses.
That's right, yeah. So I'll fix it. So thank you. There needs to be a closed parentheses after B12 and then divided by B13 there. So how many of you got 1.09? 1.09. So then what you would do, 1.09, you would then go down here. Okay, so recreationally trained, 1.09 would, that'd be more than trivial. It'd be more than small. It would fit right in here in the moderate. So we would say that fits in to the moderate category. So that would be a moderate effect, which is pretty good for a recreationally trained sample. And I just looked the other day, the Journal of Strength and Conditioning Research now requires effect sizes in your stats. So to publish there, you have to have this calculation there reported for the size of the effect. Okay, so let's go ahead and let's get the 4-minute group. Okay, so same process, right? You could just get your averages. And same process. Same process for standard deviation, STDEV.S. And you could drag it across. So you have both of them. And then the effect size is, tell me again, what is it?
Post
Yep.
minus
Post-test minus pre.
divided by.
Now remember to close my parentheses, divided by what? Yep, pre-standard deviation. And I got 1.73, so how would we interpret that? So recreationally trained, going down, that's a large effect size. So that's important to know. So where did Ray get all of these numbers? I think he was just making them up. So I'll tell you a little story. Ray was 1 year ahead of me in the doctorate program at Arizona State. So I know him pretty well. I sat by him through several classes. He was the guy on strength training meta-analytic research for a long time. He doesn't publish so much anymore, but these values were based on literally hundreds of studies where he went through and calculated effect sizes. So he wasn't just making these numbers up. He had looked at hundreds of studies with different populations and looking at effects, and this is what he came up with. So we could say that, at least in this sample, resting, taking the extra 4 minutes, or the extra time, 4 minutes between sets with heavy loads, made a difference in terms of the magnitude of the effect, is what we could say here. So, okay, so what I'd like you to do, there are two different spreadsheets here. I'd like you to work on calculating an effect size for this one. And so this was another study, mid-thigh skin fold. Okay, so you can estimate percent body fat. How many of you knew you could estimate percent body fat with just one skin fold? Okay, so you can. Pre-high intensity interval training, post-high intensity interval training. Okay, so I want you to just, same process, I want you to calculate an effect size. And then, last one for today, mid-thigh circumference, pre-squat training, post-squat training. So you can start either place, and I want you to come up with an effect size for these two studies. And once you've got that effect size, I want you to take a look at the table down here and interpret that finding. Anybody have one for mid-thigh skin fold yet? And remember, take the absolute value, right? So a lot of you are getting, what was it, negative what?
-383.
Negative 0.383. is another recreationally trained sample. So negative 0.383, take the absolute value, so we're looking at right here, so that'd be a small effect size because the absolute value is between 0.35 and 0.80. Everybody see that? Okay. How many of you got negative 0.38, right? Okay, all right, let's get to this last one. You want to make sure you save your work, save your spreadsheets, because it'll come in handy later. Okay, so 1.03, so how would you interpret that? Your interpretation, yeah. So another recreationally trained sample, that would be here. Yeah, moderate effect size, which is really pretty good. A recreationally trained sample, if you're getting moderate or large effect sizes, that means that it's worth paying attention to, regardless of whether you have statistical significance. So the purpose of this chapter is to just say, okay, well, there's more than just probability in making a decision about something. You also have to look at the actual magnitude of effects. The good thing about effect size is you have these scales available that have already been designed based on previous research. You can say, okay, well, if that's a moderate effect, that must be a pretty good change from pre to post. Okay, so what's your assignment for Thursday? Yep, the Ray article. Okay, so thank you, and I'll see you on Thursday.